Okay, good morning everyone. Today we'll be talking about boosting. Boosting is a general framework of a number of different algorithms which have been very successful, particularly one very specific algorithm which is called Adaboost. Adaboost has been used a lot in face detection, and since then it has been it's been very popular. It's a very simple algorithm. It's not so very difficult to implement, and it has a number of very interesting features. And I think it's one of the major topics in machine learning in general. So it's a very interesting thing. But there are other boosting methods, and I'm trying to talk about a little bit of all of them today. A little bit, particularly, of course, of Adaboost, because this is the major one. This is also the most simple one. Today we'll also have a little bit more of math, so I will try to derive all these formula that you need for Adaboost here on the board. I will do this very slowly, and so whenever you have some problems, you don't follow me, then you just interrupt me. I think this is much easier or better for you to do this step by step than just put it on the slide, because otherwise you would probably not understand it that easily, right? So the whole point of this is that I would like to show that there's some math behind it, but the algorithm itself is very easy, which is very, very nice always, right? So the algorithm itself should have only a few formula, and we as a developer, we should do more stuff before. So let's start first of all again with where is it? This is not on. With the repetition. And this is one slide that I showed already earlier. This is the slide on regression. So we have our typical regression problem. We define a number of basis functions, right? We have with m basis functions, and in regression we had some examples how to do this. It could be some polynomial, or this was an example of a simple basis function. We also had Gaussian basis function. For the moment, we don't say specifically what these basis functions are. We just say we kind of know that there's something like that. There's some basis function. We'll later see how we can use basis functions and which kind of basis functions are used in boosting. Now, our goal was to fit this model into the data. So we have a linear model here with some weights. These are the parameters that we'd like to estimate from the algorithm. And these are the basis functions, right? And we are given some data. So we have some x, and we have some also output y or t, what we called. This is our model, and our model should now fit into our data, right? If we're in our t output data in a certain way. So that means what we have to do is we build up this error function here, e of w. W are the parameters again, and we'd like to minimize this error function, right? And what would be in this particular case here, we minimize the squared error between our model prediction and our true data, right? This is the true data here, ti. So we simply sum up the squares of this, and then would like to estimate this and minimize that. This is the general formulation of regression, where this error function is now, of course, a specific one, and we can think of now doing different error functions here. Now, to find the optimal parameters, as I said, what we do is we derive this with vectors w and set the derivative to 0, and we already know what comes out of that. Now, some questions to that. First one, can we do the same for classification? Right, this is one major idea here, because regression and classification are not so different, right? There's only this little difference that the target space where you map into is discrete and is not continuous. So we have labels instead of real numbers. So we could probably think of doing that for classification as well. For example, if we consider only two classes, right, then we have the binary case. We say ti is just a member of the set of -1 or +1. Right? We just have two classes. -1 is background, and +1 is the object we'd like to detect, or for example. Then the second question is, can we use a different, better error function? Right? This error function here is good, but we'll see that there are some problems with it, and we might have to think of some other kind of error functions here. The third question is, and this is a very interesting question, can we learn the basis functions together with the model parameters? So can we do we find some basis functions which are kind of very good for us, but we also find at the same time parameters for our model. And the last thing, which is probably even the more important one, can we do this whole thing sequentially, right? So instead of like doing this all at once, we add basis functions at every round, right? So we start training with a first basis function, we do some optimization, and then we find, hey, we need some other basis function to even be better in our model, right? To minimize our error function, we go adding new basis functions to the whole process, and by this we get better and better and better with in terms of the error function. This is the major idea here, right? Instead of having this all at once, all the basis functions given at once, and optimize all the parameters at once, we show the algorithm more basis functions and optimize a new basis function according to this error function here. So the answer to all these questions is yes, we can do that, and we do this using boosting. First of all, let's talk about loss functions. The definition of a loss function is a real valued function, L, where of t and y of x, where t is a target value and y is a model. This is called a loss function, right? T is our known data. This is what comes out of the process that we have. We have x and t's given, and we have a model, this y of x, which we like to estimate, and the L function is simply now how far are we from the true data, right? How far is y of x from t? And in general, now we can say L can have many different ways, right? Many different shapes. So one, for example, is the so-called 0-1 loss, which is a very sharp differentiation, right? This is simply if then else. If t is equal to what is predicted from the model, then I say it has no loss, right? So you have to really think different. It's bad to be, if L is big, that is bad, right? We want to have small values of L. So there's no loss here. This is perfect. But there's a loss if this is not true, if t is not the same as y, because then we have an error in our prediction, and we say now we have a big loss here. This is the so-called 0-1 loss. Then we have the squared error loss, which this is the one that we just had in the slides, 2 slides before. So this is the probably most intuitive one, where we say, hey, we just want to have the squared distance from our model to our data, right? But you could also think of other losses. For example, this one here is the so-called exponential loss. The exponential loss simply multiplies t with y of x, where, of course, you kind of assume in this particular case where we do binary classification that t and y are both either 1 or -1, right? So what this actually means is simply I take, so if they're both the same, right, then this product here is positive, and if they're not the same, then this product is negative, right? It's just the common sign of both, you could say, right? If t is -1 and y is -1, then of course the product is 1, and then you say, then you have this, right? So let's see how this looks like, and I think this is now a general case. You could also think of having this not -1 +1, right? So the general case is this here. We have now plotted all these 3 loss functions. The first we see is that the 0-1 loss is not differentiable, right? So if we would like to minimize this loss function, then it's hard to do that, because at this position here, we don't have a real derivative. It's hard to find the derivative at this position, and it's not so easy, right? Also, even here, the derivative is 0. So if I start here, the idea is to start at some point and then go towards the minimum of that loss function, and there's nothing you can do, right? This is very hard to minimize analytically. Now, the next thing is the squared error loss that we just had also before. This is just our squared error here, which is nice, but it has only one optimum here, right? So it's not really clear why this should be better here than here, right? So, also what I have to say is on the x-axis, you see just the product of t and y of x, where y of x can now be a real number, right? It's not just 1 and -1. This can be any number, and t can be +1 and -1. So this just means if this value here is very high, then our prediction is very good, right? This is just our intuition about this, right? T times y is high when our prediction of the model fits very well to the data. That means the higher this value is, the better we actually are, right? The better we fit to the data. And the squared error loss will then be worse again at some point, right? This is not really very intuitive. However, the exponential loss here, this actually is much nicer, because it kind of goes smoothly towards 0, right? the farther I'm away from 0, right, the better my prediction is, the smaller is my loss, right, which is exactly what we want. So now let's think of using the exponential loss instead of the squared error loss. And now let's find a way to minimize this exponential loss sequentially. Now, sequential fit in a basis function, how can we do that, and what do we mean by that? So the idea is we start with some basis function phi 0, right? We just assume we have some basis function given. We have our model here, so we have a W0. And then at each iteration, we have now iterations m. We add a new basis functions phi m to the model, right? So that means we have this whole thing, which is the same as the previous one, plus some add-on, plus some new basis functions with some coefficient here, Wm. Now, 2 questions we have to answer. How do we find a good new basis function? How do we find a new phi? And how can we find a new good value for Wm, right? These 2 things now need to be specified in every training round. And the whole idea is to do this by minimizing the exponential loss function. And we'll do this now really here live. Now, this is our aim again. So this is our error function, right? We write this down again. So we have our aim Wm, phi m, so that these 2 minimize this whole error function. And our error function is this here, our loss function is this here. And I'm now trying to do this here on the board. And you just interrupt me when you can't. So just copy this again. So we have our Wm phi m equals argmin of W and phi of, and now we have the sum over all data points, right? And we use our loss function. This is T of I, Ti, y m minus 1 of xi plus W phi xi. Right? I hope I did this. No, only two parentheses here. Right? So this is just the previous model that we assume to have already in the mth round. We say we know the previous number of basis functions. We just want to add a new one. And here there's no index m because we want to find the one that minimizes that. So we want to find the phi and the w so that this is minimized, right? Now what we can do now is we say, okay, let's use our loss function. We now plug in our loss function here, which is the same as argmin w phi, again our sum. And now we say L is the same as exponential of minus t times y. This is the same, or exponential of minus ti times, and now we have this sum minus 1 of xi plus w phi of I xi, and now we have the 3. Right? So we just plug in our definition of the loss function. And now we can do this a little bit simpler. We can say this is argmin w phi, again our sum. And now we see there's a sum inside here, a sum inside of the exponential, and we can write this as a product over 2 exponentials. We say this is minus ti times y m minus 1 of xi times the exponential of minus ti times w phi xi. This should be correct. Right? What I simply did, is this clear what I did? I simply wrote the sum as a product of 2. Now the first observation we have to do now is that this term here does not depend on w and on phi. Right? This is just what we kind of assume, which is given already from the previous training round, m minus 1. So you can call this thing VIM. Right? This is a value that depends, of course, on our data points. For every data point, I have a different one, xi. But also in every training round, I have a different one. So in the training round m, I have a different value here. Right? This is just a value, a factor in front of our exponential here. Right? And now what we also do is we name this whole thing E of W and phi. This is our error function. Now the aim is to write this error function in a bit nicer way and derive this error function with respect to W, and also to find a phi that minimizes that error function. So let's write this down again. E2 of W and phi equals, now let's make it a bit simpler, our sum E VIM, and we write this a little bit different, only like this, minus W times Ti phi of Xi. Now, we have this thing here. Now we have to do a case study, or a case distinction. We have two cases here, two cases. The first case is that Ti equals phi of Xi. And the second case is Ti does not equal this thing here. What does this mean? So we know that Ti and Xi and phi I, they're both binary. So this is either -1 or +1, and this is either -1 or +1. So there's only four cases where what can happen here. And from these four cases, we can distinguish two of them. They have the same sign and have different signs. If we call this thing here P, right, to make it a bit simpler, then in the first case, what we have is that P equals exponential of, so if this is 1 and this is 1, then the product of them is also 1, then we have this is equals minus W, right? Because then this is 1, this is 1. So if the signs are different, then the product of the signs is -1, and the whole thing of this is actually plus W, right? These are the two cases. Okay, now what we can do with that is we can split this whole sum up. This is kind of the little idea. We try to split the sum up, and we say this is equal to the sum over all cases where Ti does not equal phi. This is the cases where our predictor is incorrect, right? This means our model does not give me the right answer. Yeah? This is our ground truth, Ti. This is what the model gives me. This is not the same, right? This is the misclassified samples, misclassified from our basis function. Our basis function tells us the wrong thing, right? Right? So then I can write this down again like this here, exp of, and now I have this thing here, minus W. Right, this is the one case. Plus the other case, where this is exactly not true, where they actually do coincide, right? This is VIM of exponential of plus W. These are the two cases. Yeah. Now the trick is to write this again down in the sum of over all n. So the first thing we can do is we can now introduce the so-called indicator function. The indicator function is just written as an I, and indicator function of A is 1 if A is true and 0 if A is false. Right? So this is the indicator function. So that means we can write this first thing here, right? This is the sum over all misclassified. We can write this as a sum over all n of VIM of indicator function Ti not equals phi xi times exponential of minus W. Right? This is exactly the same. This is kind of clear, this step here. This function here simply says, if this bool value here is true, then this function here is 1. And otherwise it's 0. That means in the case that our prediction is right, I only add zeros here. Right? I take 0 times 0 would be 0. So in all the data points, this is goes of all data points. For all data points where our prediction is right, is correct, this whole thing is 0. And for all the others, this is 1. So I'm still only adding the misclassified ones, the misclassified data points in this case. Right? Plus, now I need, of course, to do the rest. Before I do that, let me do a little thing. I put this exponential here in front, right? This is a slight, sorry for that, but it makes things a little bit easier then. So this exponential of minus w, I just put in front because it doesn't depend on the data, right? It doesn't depend on I. This is just a fixed term I can just put in front of the sum. Right? The same I do with the other one. I do exponential of w. So this is e to the w, e to the w. And now I do another little trick. Now these are the correct classified ones. And express the correct classified ones in terms of all minus the incorrect ones. Right? So what I do is I do again a sum over all I equals 1 to n times y v I m. Now I have the e to the w in front. I don't need that anymore. Minus, this is all the ones. This is just all the cases for all data points. Minus, and now do again a sum. And now just copy the incorrect ones. These are the incorrect ones. Right? Is that kind of clear what this means? This is just a term here. This is the sum over all data points where our prediction was wrong, right? Where we have misclassified examples here. Right? These are the wrong ones. These are all. That means all minus the wrong ones are the correct ones, which is this term here. Now let's go on. Let's rewrite this a little bit different here. We go here. Now we subsume this term and this term, right? We say this term and this term can be put together. We say now what do we have in front? We have, first of all, we have e to the w. E to the minus w minus e to the w times this here. Vim ti does not equal phi of xi. So this is just this term here and this term here together. Plus, of course, we need now the rest, which is e to the w times sum over Vim. So now this is our error function. It's still just our error function here, right? It's nothing else than that. Let me check if this is correct. There's something wrong there. Something is wrong. Either the minus. I think I have the signs just wrong. The signs of W. These are the correct ones. Of course I have it wrong. No one told me. The incorrect ones have plus. These are the incorrect ones. Right, exactly the opposite. No one told me. You're not paying attention. So this should be plus W for the incorrect ones, and it should be minus W for the correct ones. That means this just turns around. This is e to the W, this is minus W, and this is e to the minus W. Okay? Yeah, these are the two cases. These are the incorrect ones. For the incorrect cases, P is equal to e to the W, not to the minus W. Now, this is now an error function that looks a bit, let's say, easier than this thing here. What we do now is we have to do two things now. We want to minimize this thing, and what we don't know is phi, and what we don't know is w. And what the algorithm does is now in this, let's say we're in the mth training round, we're still in round m, right? We have we think that we know some parameters vw already, these things here, and we now have to estimate w and phi. So this is known, and this is unknown, this is unknown, and this is unknown, and also this is unknown, this is known. What the algorithm does now is it finds a phi that minimizes this whole thing. And we're not saying at the moment how it does it, right? It just says, first of all, we need this thing here. And I think this is also the next thing on the slide. So the first thing we need is to find a phi m that minimizes this term here. Because this is, of course, independent of phi. And so to minimize this error function here, the first step we do, find a phi that minimizes this thing here, which is nothing else than the weighted sum of the misclassified data points, right? We just sum of our data points, weight them by some kind of weights. So we have to assume that there's v values in front of our data points. And we sum this up, and then we find a phi that minimizes this whole sum. That's the first step. Now let's assume we have that. So we don't care about phi anymore. The next thing we do is we care about w. So what is the good w to find here? Well, to do that, we derive this whole thing. We say, what's the derivative of e to the w and phi with respect to w? Well, this is just this thing. This is e to the w minus e to the minus w. Sum plus ti not equals phi minus e to the minus w. Right? Is that clear to everyone? I hope it's right. It's just derivative of the exponential function is just the exponential itself times the inner one. Here is nothing to do. Here we have a minus sign in front. We put the minus sign in front. The same here, minus sign. So we just switch signs. And this whole thing should be 0, right? We want to minimize the partial derivative with respect to w. What we can do is we say this should be the same. So I like doing that. Sorry for the wiping. And now to do that, we just divide by these two terms. We divide by e to the w. We say this is e to the w minus e to the minus w divided by e to the minus w. And we divide by this. We say this is the sum, which is the misclassified ones, divided by the sum equals 1. This is kind of an unusual way of doing that, but it kind of gets clearer in the next. So what this simply does is I divide by this sum, I divide by this. So I have this term here. Now what I do is I make this simpler. I call this is error at round m. Why is this called the error? Well, this is simply a weighted sum of misclassified data points normalized by the sum of the weights. Right? So if I interpret this v as a weight in front of every data point, then what I simply do is I count how often do I misclassify and sum the weights that correspond to these misclassified data points. Right? These v's here are weights. And I sum all the weights and divide by the sum of all weights. Right? This is just a normalized way of expressing the error that my phi function actually does. This phi is a basis function, or can also call it a classifier, right? Predicts a model, and whenever this thing is wrong, I add something to my error. And if it's often wrong, then the error is high, and otherwise it's low. So this error here is just a value between 0 and 1, right? In the worst case, everything is wrong by phi, and then everything is wrong, and then error is 1. And the best case phi is perfect, and then this error is 0. And this thing can be expressed by e to the 2w, sorry, there's a plus 1. Right? So this is just simplifying that. We have this equation now, and we have to solve that for w. Is it okay if I just do this in the next step, or should I do one step in between? Let's do one step in between. We say e to the 2w equals 1 over the error minus 1. Now we express 1 as error. We say this is the same as error divided by error. That means w is 1/2 of the logarithm of 1 minus error divided by error. Right? So what I do now is, in the mth training round, the first thing, what I said already, the first thing is to find a good phi that in some sense minimizes me this here, right? This phi m. Now once I have the phi m, I can compute the error that is produced by this phi m. It is this thing here. I have now the phi m, I plug it in here, I compute the error of that phi m, and once I have the error of that phi m, I can compute w. The only problem now we have is we still need to compute v, right? These values here are now, they're given from the previous round, but for the next round we need to find them somehow, right? We need to compute them in the next round to be able to do this iteratively. So the last thing that remains to do is to compute, let's do this here. What is vi m plus 1? And to do that, we first start with the definition. This was the definition of VIM, right? We said VIM is this term here. So what is VIM for the next round then? Well, we just put in m plus 1 in here. We see this is the exponential of minus ti times y of m of xi. All right. Now we plug in the definition of ym. Ym was there. Or yeah, ym is simply exponential of minus ti times ym minus 1 of xi plus wm phi m of xi. Third one, yes. Now we do the same thing again as before. We write this as a product. We have this ti ym minus 1 of xi times exponential of, and now switch already these two things, wm times ti times phi m of xi. Now this is nice because this is our definition of our previous round. This is m, right? This is VIM again. Which means that in the next training round, our weights that we assign to every data point just have to be computed from the previous weights, right? We assume we know these already. We have to initialize them somehow, of course, but once we initialize them, in every training round, we compute VIM plus 1 from VIM. And now we have to know a little other thing here. This is again the same thing as before. We have now this case analysis. We have to now find two cases where what happens to these two signs. And the way we write this, we can say the sign. Let me say, let me look at these cases together. So if this is if these are the same, then we have exponential minus w. Otherwise, we have exponential plus w. So we express this in terms of, again, of our indicator function that ti is not equal phi of xi. And to compute from this function that goes to 0 from between 0 and 1, to compute a sign from that, we do 2 times that minus 1, right? So if this is incorrect, yeah, then we have 1 here. That means we have the sign that we have is +1. Is that right? So if it's incorrect, yes, then the sign in front of our W is +1. Right? So this is the sign of everything in front of W. Right? This is the sign of minus TI. Yeah, just the sign of this. Because if this is wrong, which means that our classifier is correct, then this thing is 0, and the minus and the sign is -1, which is here, which is true, right? In the case of a true classification, we have a minus in front of the W, and the other case we have a plus in front of the W. So now we just have to use that term and put it in front of our W. That means this thing here equals, this is equals to 1 times exponential of 2 times indicator function Ti is not equals to xi minus 1, and of course W is missing, times W. Now this is again a sum. That means that we can do this like this. Exponential of 2 times indicator function Ti not equals xi times W times something like this here. Yeah. Now what we do is we compute our new VIs from the old VIs and from our given W. W is now already given, right? In our training ground we know how W looks like, which is just this here. Which is interesting because here in front of W there's 1 over 2, there's half, and there's a 2 here, which means that we can cancel that out later in the algorithm, right? We don't need to do this here. That's one thing, if we plug W in here. And the other observation is that, and that's very interesting, I have a little thinking about this, this VI here, if we use that in the next round, where do we put that in? Right? In the next round, what we do is, let's assume we compute this VI m plus 1, and we do now the round m plus 1. In round m plus 1, we have to again compute all these things. We have to find another phi, but we also have to find another error. So we have to compute this error function again for the next round m plus 1. That means that this thing here, this VIM plus 1, goes in here and in here, right? Because we just plug this in the next round. And that again means that this is a fixed term here. This exponential of minus Wn appears here and it appears here, and it's independent of the data points, right? We can then again put that in front of the sum here and in front of the sum here, and we can cancel it out. Which means that we don't need to compute it at all. We don't even compute it, right? Because anyhow in the next round it will be cancelled out. Sorry? Okay, this term here, right? This is a constant factor that is independent of the data point in front of our weights. So every weight will be computed from the previous weight times this here, right? Well, this depends of course on our data points xi and ti, right? This thing is just a constant factor that we know already because we know W already, and it's independent of our data points. Now what we do now is we use that thing here, and let's say we're in training round m plus 1, and we'll see this right now in the algorithm. This is then easier to understand probably. In the next training round m plus 1, you use that definition of your weights to compute the error, right? Because you have to compute the error again of the new one. That means you plug this definition here of VI m plus 1, you plug it in here, just with a plus 1 here and plus 1 here. Yeah? But then what happens is this exponential here is independent of the data points, so you can put that in front of that sum, put it in front of that sum, and cancel it out. And if it's cancelled out, then you need to compute it, right? Because it's something you don't need to do, right? It's sufficient to define your weights without that. So this is just to summarize. This was our data, our weights that we need to compute. And we see that the weights depend on the error, right? So we have to compute the error first. Once we have our new basis function, we can then easily compute the error of that basis function. We just look at how well does it predict. Does it have a big error or a small error? And once we have the error, we compute the weights. And also what we have to do, we have to update our, these are different weights. These are weights for the classifier, right? For the weak classifier phi, we have a weight W here, right? And these are the weights for the data points, right? And what we do is, this is kind of the intuitive thing, the data points are updated so that all the ones that are misclassified get a higher weight than the other ones. So if phi misclassifies something, then this thing is non-zero, and then I actually do some update here. Otherwise, if phi does give me the right prediction, then this is 0, and e to the 0 is 1, which means I don't do anything with that weight. Right? So imagine I have, for every data point, I have a different weight here, and my phi predicts me that data point perfectly. So it gives me the right answer. In that case, this whole thing is 0, and e exponential 0 is 1, so I don't change that weight. But if this does actually differ, so if the prediction is incorrect, then I have to add some weight to that data point. And the idea behind that is just, in every training round, I just add a new training classifier. But then I look, where does this classifier fail? And only those cases have to be looked at in more detail in the next round, training round. And I do that by updating their weight. So the whole algorithm is this here. This is just a summary of Adaboost, which does nothing else than just these equations, right? It's just that. So we initialize first all our weights. That's important, of course. For all vi have to be initialized. Every data point gets the same weight in the beginning, 1 over n. Then we have capital M training rounds, right? And in every training round, the first thing we do, we fit a classifier. We call this a basis function, or in Adaboost it's called a weak classifier. We fit a classifier that minimizes this thing here, right? The weighted sum of the number of incorrect classified data points, right? This should be minimal. Once I have that phi m, I compute the error that's produced by that phi m, right? I can just say, now I know this thing, I can now just normalize it by the sum of all weights. And I've defined this alpha m here, which is nothing else than 2 times w here, right? This w here is alpha m divided by 2. Alpha m is just more convenient because anyhow, when I plug this later in here, I don't need to do this 2 times anymore, right? This 2 then goes away. That is just the reason why I introduced another notion here of alpha, another symbol here, right? So I compute alpha m, and then once I have alpha m, I compute the new weights. I just plug this alpha m here, or the w here. Here, this goes in here, right? 2 cancels out. And now I have everything in place to compute the new weights for the data points. This is just that. And I do this all over again, right? So this is just, I have a number of training rounds. At some point I stop. And in the end, once I have done all these iterations here, I use this as a classifier, right? Which is simply the sum of all weighted basis functions, right? Now I know all my coefficients in front of the basis functions, all the alphas, right? And this is very similar to regression. This is just a linear additive model where we just add basis functions linearly with a factor in front. And for classification, of course, I did classification, so I know that this gives me a value here, which does not have to be exactly 1 or minus 1, but if I use the sign of it, then I can say this is class or not class. Okay, is there questions? Can you repeat the question, please?
Is it only about given a model and we want to add a new decision
Yeah.
to it?
Yeah.
Then all the entire model gets.
Yeah. So this algorithm does not say anything about how the files look like, what kind of file you use, and how you find the best file to do that. That's the nice thing about it, because it's a very general algorithm, right? It generally says, if I have some kind of basis function, some kind of weak classifier, as we call it, then I can use that to minimize the loss function in every training round. And that's the reason why it's called boosting. The boosting algorithm reduces the training error in every training round. And you can do that as long as you want, right? The longer you do that, the better you get, because the exponential loss function just goes down and down and down all the time. Of course, at some point you say, I'm too close, I fit too perfectly to the data, and I don't want that, because then you overfit, right? But interestingly, boosting does not overfit that much, right? There's many discussions around that. Why is this the case? People for a long time didn't really understand what's going on here, because it should overfit a lot, but it doesn't. It does overfit, but not in the way, or in the way people would expect it to. So that's the nice thing about it. It's a very nice framework to, and that's called the reason why it's called boosting, right? You have your classifier. This phi m is already a classifier, right? It's a very simple classifier, but it's already a classifier. But it's not very good, right? It can make errors. But using boosting around that weak classifier, you even make it better. So this phi classifier gets better and better and better on the training data. And interestingly, it gets as good as you want it, right? So this is the nice thing about it. You boost your weak classifier. And weak, just to, I think this is the next slide. Let's do the next slide, and then we have a small break. The basis functions, that can be any classifier that can deal with weighted data. So we can think of anything that we fit into the data where we have weights in front of the data points. So important is that if these base classifiers provide a training error that is at most as bad as a random classifier. This is one, let's say, theorem that is related with boosting. So if we have, this is called a proper weak classifier, right? Proper weak classifier is a classifier which provides a training error that is not worse or at most as bad as a random classifier would be. A random classifier for a two-class problem is, of course, 50%, right? So if you just sample randomly labels to the data, then on average you will have a training error that is 50%. That means if you can guarantee that your weak classifier is better than that, which shouldn't be a big problem, right? Because otherwise you can't do classification at all, right? If you have a classifier that is worse than random, then why would you do this at all, right? Why would you do learning at all? Then you can't do this. But let's say you have a way to find a weak classifier that gives you training error of maximum 0.49, something like that. Then Adaboost can return an arbitrary small training error in every. So you can, the more training rounds you run, it gets better and better in every training round, right? And there's some possibilities for weak classifiers are decision stumps and decision trees. We will have this in the next hour. I'll say more about that. Okay? Okay, let's go on. We were talking about the basis functions. These are the weak classifiers. And now would like to have a kind of closer look into possible weak classifiers. And we look at these two possibilities, decision stumps and decision trees. They're not so much different from each other. One is just a very simple version of the other. And the simplest version is decision stump, or yeah. Decision stump are a kind of very simple weak classifiers. And the goal, what you have in this decision stump, is to find an axis-aligned hyperplane that minimizes the classification error. So if you plot your data in this way, for example, you have a two-dimensional problem, right? Every data point is a two-dimensional vector. It's a very simple example. Then what decision stumps do, they look at every feature dimension, right? This is dimension 1, dimension 2. And in every dimension, they look for a hyperplane, right? In this case, a line that separates this data in an optimal way. An optimal just means that you minimize the classification error. And the way we do this is, you can do this very simple. You just look at all the possible positions of this hyperplane, right? You start with this line here, and you go here, and for every data point that you have, you just put the line just behind it, right? Or at the position where the data point is, right? You have a number of possible positions where things could change. And in all these positions, you simply count how many do I have on the left side and how many do I have on the right side. And then you just look at how many wrong ones do I have on both sides. And you sum up the wrong ones. For example, you would have 2 blue ones on the left side, which is wrong. And you would have 3 right ones on the right side, which is also red ones on the right side, which is also wrong. So that you then would say your classification error is 5, for example. You could do something like that, right? This is a very, very simple classifier. But the whole idea of it is to be better than random. And you can show that this thing is definitely better than random, right? For every data point you have, in general, if you apply this strategy here, then you will always be better than 50% classification. Yeah, and you do this, of course, for all feature dimensions, and of course you take the dimensions where your classification error is the least, right? Okay. This is just an example how this looks like. We have some data here, some blue and red data points. And in training round 1, you just say you look at your best separating plane, and your decision sum says, well, this should be the plane where these 2 data classes are separated the best, right? Now in the next round, this is training round 2, this is the interesting thing about it, you give higher weights to the misclassified data points, right? So here look at, let's say, the left part is the blue, should be the blue prediction from the classifier predicts this as blue and this as red, which that means that these points here, this point and this point and this point, they are misclassified by the reclassifier. Which then means by Adaboost, I give a higher weight to these ones, and I keep the weight of these. Of course, this is not right here, right? The weight here seems to be smaller, which is not right. It's not correct. This should be the same weight as before, and this should have another weight, a different weight. Of course, I think what this means is here you can also normalize the weights, and in relation to these weights, these are much smaller. So if you normalize the weights in every round, then of course they will be smaller. But this is just to show you that these are the more important points because they have been classified incorrectly, and I have to find a new classifier that separates these better than the others, right? And again here, right? These blue ones are also misclassified by the classifier, and I would like to find now a plane that separates these well. And of course, this plane doesn't have to be in this dimension. It can be in the other feature dimension, right? Have many feature dimensions. I can also find planes that go like this, that separate data well in this case. Well, if I do that, then this class will be then I have again a reweighting, right? These points again all correctly classified. These are correctly classified by the second one, but wrongly by the first one. So they have a smaller weight, but not as big, as smaller weight as the first ones. And these are completely misclassified by both weak classifiers, so they have an even higher weight, and so on and so on. So after 6 rounds, you can see that the decision boundary, the overall decision boundary, which is just a sum of hyperplanes, right? It's just a sum of lines in this case, will then adapt very, very smoothly around the actual border between the two classes, the boundary between the two classes. I think I have, yeah. And after 150 training rounds, you will have something like this here, right? Where you have really a perfect fit around two classes, right? At some point, of course, you always have there's still some misclassifications here, but at some point you won't have this anymore, right? Yes.
So at the end, if I had a new data point,
Yeah.
I can say if I find the area, okay, it's blue or it's in this case red.
Yes. So the thing is, that's a good question. If you have a new data point, then you simply apply all these 150 weak classifiers that you found, and sum up what they say, and this is then your classification, right? This then gives you the prediction of the new data point. Yeah. Yes, that's right. That's right. So it completely overfits in this case. But as I said, in general, it doesn't overfit that much, right? For whatever reason. So there's analysis on that, but it's still a very good algorithm, right? And it's very nice to look at this. Yeah, but of course, I mean, at some point, every boosting algorithm would overfit. Now, this was decision stumps, and now you can extend that idea to decision trees, which is basically the same as a decision stumps, just with more levels, right? Or set the other way around. Decision stump is just a tree of level 1, of depth 1, right? You do the same thing again. Now you say you decide on a certain feature in feature space, right? You say x1, x2, and you have more features. If x1 is smaller than this threshold, then you go to the left tree, and if it's bigger, then you go in the right tree, and you can do this in all kind of feature dimensions, right? You have this kind of tree here, and you can plot it like this here in this case, where you have 2 dimensions, x1 and x2, and yeah, according to in which subtree you jump, you just go there, and you have a different value there, right? This is of course regression, but you can do this also for classification, where you just say this is 1 or -1, right? Now we call this classification and regression trees, CART, right? And this is just the same thing for classification, right? Where you have 2 features, color and shape and size, for example, 3 features. So you can now first distinguish these objects by color. You say if it's blue, then it's definitely then there's 4 objects that are blue, right? If it's red, then you have to distinguish shape, right? Because you don't know. Like that's the interesting thing here. This says 4 on the left side and 0 on the right side. So 4 labels yes and 0 labels no, which is then sufficient to stop here, to not grow the tree anymore here, because now you have all objects that are blue are on the left side. So this is a classifying feature already. You just need blue. But if it's red, then you have to look at more things, not only color but also on shape, right? You say, well, if it's an ellipse, then there's one case here and one case here, right? This is, of course, not, again, not perfectly classifying, but you have at least a distribution, right? In this case, you still at least say, hey, if it's shape and ellipse, then I have a distribution over 2 classes, and in both classes there are red ellipses, right? So this is just to give you an idea of how this looks like. And then, of course, if it's not an ellipse, then you are certain that it should be class no. And the same here for the size. So what we store here is in the leaves we store this distribution of y equals 1 given x, right? And for example, for the case of an ellipse, this is just 0, 5, right? Now, how to grow such a tree is a very hard problem, right? To find the optimal partition of data is an NP-complete problem, right? It's not so easy. You can imagine that is what you have to do is, in general, if you have many features, then you have to find all kinds of combinations of features in trees. So every order of features gives you a different tree, and then of course the tree size varies and stuff like that. So this is not so easy. There's a greedy strategy you can use. You use this function fit tree. So you do class label prediction. You split the tree into 2 subtrees at a certain feature. Then you have some measure that tells you if it's still worth splitting like go on splitting. For example, if you don't have enough data in the subtree, then you stop splitting. You say there's not enough. I can't reason on this. And if you do some splitting, then you add the new test, right? You found a new threshold T star that defines the node of that level in your tree. This is then your test. And then you go on recursively. You call fit tree again for the left node and fit tree for the right node. This is just a greedy way of growing decision trees. The split function here finds an optimal feature and an optimal value for that feature, right? This is basically exactly what the decision stump does, just repeated, right? And a number of. And for classification, it finds a split that minimizes some cost function. For example, misclassification. This is just your way of minimizing that cost function. Decision sum is nothing else in decision tree with depth 1, and there's different stopping criteria for growing the tree. It can be reduction of cost is too small, the maximum depth has been reached. So of course, imagine again if you don't allow a maximum depth, then you again overfit, because then your tree is like perfectly fits to the data, and you have like in every node of the tree you have either class 1 or class 2 or class -1, and then you would of course perfectly predict your training data, but you would not be able to predict new test data, right? So you have to find a maximum depth of your tree. Then the question is, one other criterion is if the distribution in the subtree is homogeneous. So if it's like well balanced or not. Is the number of samples in the subtree too small, for example, then you also stop, right? These are possible ways to stop splitting. And then of course, once you have built up the tree, then there's ways of pruning that tree, right? There's another idea to do that. If it grows too large, then you can again overfit. And to do that, you simply stop the grow. Stopping the grow can lead to situations where the tree is not expressive enough, right? This is also possible sometimes if you just stop. So another idea is to just build up the full tree and then prune it again. And you can do this with cross-validation. You just say which are the features that you actually don't need. One also important algorithm which is very popular nowadays is the random forests algorithm, and this is just another extension of that. So it uses not a single tree; it uses a number of trees, and it also uses randomization. So here, there's just a number of facts about this. I'm not saying much more about this. There's something in the book about it. I think what you only have to know is that random forests, they have two kind of random things. One is the order of your features, or also the feature that you actually use, and also the order. So both is there's kind of a randomization in that, which helps in reducing overfitting, and it's also very efficient to do that, right? So you just sample randomly different features, but you don't take all the features. What the random, that I don't know. I can't say much more about this, right? This is just one slide, and I don't think you need more. No, you need more about this, because also in the book there's not much in that, right? So. You were saying that we need to have a randomization feature, like. Yes. So the idea is that if you have one tree where we have some random ordering, which is probably not the best one, then you might have another tree that has another better ordering of the features, right? So you have a number of trees, and they are all sampled randomly. So you have this random forest thing, and and this makes things more efficient, reduces overfitting, and it's very fast to do. Yes, yeah, of course. These vote then together into one. This is probably the same idea as voting or something like that. Yes. Okay. Now back to boosting. We have seen that Adaboost performs very well, especially when we use decision trees or decision stumps as classifiers. However, if we look at the loss function that we actually minimize, which is the exponential loss function, the misclassified examples, they're weighted very highly. That is a little bit here. Where can you see this? The black curve here is the Adaboost, and this is the number of training rounds, and this is the test error. That means this loss function doesn't really. It can be probably can even be improved if you use a different loss function. And this is, if you look at the loss function itself, then you see this already, right? So again, the pink dotted curve is the exponential loss function, which is minimized by Adaboost. And what the problem is with this loss function is that misclassification, also means the more I go to the left, I'm more wrong, right? I'm more on the misclassified side. The more I'm misclassified, the higher I have this loss function. So if I have small outliers, which are very far away from zero, which means that the product of a label and prediction is very low, right? Of course, in binary equation this is not true, but if y is some prediction that gives you a real number, and if this real number is, for example, positive, and my label of my true data is negative, if this value is very, very low, very, very negative, then my prediction is very bad. But it could be that it's only this one example, right? So this is an outlier. Like this one example is predicted very, very badly, but the loss function would be very, very high, right? And this is not what we want, right? If only for one single data point which is misclassified, we don't want to be the loss function very high. And the way to reduce that is to use another loss function, which is called the log loss. So it's very similar to the exponential loss, right? It has actually the exponential loss inside, but it does +1 and takes the logarithm of that. And this means that in the limit, this is actually a linear function here, right? The more I go to the left, the more it gets linear. And this leads to another algorithm, which is called Laget Boost, which is probably not exactly the same. It has little subtleties which are different, but I'm only summarizing this here. So you have you go again, initialize your data points, your weights, right? You have, for every data point, you have a different weight. You also now have probabilities. This is also a strength of this algorithm. Now you can interpret these weights or some part of the weights that you assign to the data points as probabilities. And if you do binary classification, then in the beginning you assign these probabilities to 1/2, right? You say the probability of every data point to be class 1 is 1/2, right? Then you go over the training rounds. In every training round, you do compute the so-called working response, right? I'm not going into details why this is true. This is just the algorithm, right? This is just how this works. You can see that you do now, you look at how far is your probability from the true label. And you divide this by these weights here, which are, again, where you take the probability into account. So that means in the very first round, this VI, these weights here, they are 1/4, right? This is 1/2. 1 minus is another half here. A half times a half is a quarter. So this VI is a quarter in the beginning. But then it gets updated in every training round. Now, again, you do this here. But now, this is not a classification here, this phi m, but it's a regression. Because now you have Zi, which are real numbers. And you simply find a function that minimizes this error function here. You find a phi that minimizes this error, which is nothing else than regression. With the only difference that now we have a weight in front of this here, right? Before we minimized this without the weight, but now for every data point we have a different weight, and we have to cope with that. And I'll say this in the next slide. Now, once we have this phi, we simply add this phi to our big sum of weak classifiers, of regressors. In our case, this is now regression, right? And of course, we have to find a way how to, now these are functions, how to find a way to sum up functions, but if these are linear regressions, then it's easy to sum them up, right? And we, of course, we update the probabilities, yeah? And this is, again, as I said, it's a nice way of interpreting this as a probability of this data point. And we do this over and over again. And in the end, we do again the sign of the sum of our weak classifiers. Questions? Yeah. Can you please explain the log loss function again? Yes, the log loss function. Yes. This is the explain it. Why you use that? This is this function here, the very light blue function here.
Okay, and I don't know, I get not the point how for example, if I had an outlier,
Yeah.
how it looks then, and
Ah.
I would have no outlier.
If there's an outlier, let's say there's an outlier very far here, then the log loss does not give you a very bad value there. It doesn't penalize it very much. But the exponential loss gives you a very bad value there. It says, well, I don't want that at all, even though it's just 1 point, right? You wouldn't care about. I mean, at some point, if it's very bad here, you don't care how bad it actually is. You just say, hey, right? Okay. Now we said we need now a function, a regressor here that minimizes this error function here. How can we do that? Well, we can use regression. We know how regression looks like. We did that already. With the only difference, we now need to add weights to our data points, and I think we did that already. I think I showed this in the exercise, but I can show this again here, right? So we have again our error function, and the only difference that we have now is these VIs here in front of our squared sum, our squared distance difference here. And if you write this down, if you want to do the same as we did with linear regression, then you have to find a matrix phi hat, and this phi hat is simply v squared times phi, where phi is our matrix from the standard linear regression, and v is simply the diagonal matrix, where on the diagonal there's the square roots of the weights, right? This means that the weights should not be negative, of course, right? So if you have positive weights, then we can compute this diagonal matrix. We multiply it with our phi matrix that we have, and we have a phi hat function. And then everything is the same as before. We just compute the pseudo inverse, and we get our parameters, our model parameters. Now there's another version of boosting, which is called gentle boost. Also, this I named this for completion. The facts about this are it's numerically more stable than Laget Boost, and it tends to perform slightly better than both Adaboost and Laget Boost. Right? It's a slightly different way of doing that. Again, we initialize our weights. We do m training rounds. We find a regression function, again with weighted least squares, and then we update our regression function. We just sum them up. And we update our weights and renormalize that, right? And as an output, we get the classifier of the sign of the sum over all weak classifiers. And yet another boosting algorithm is called gradient boost. And I'm showing that because it's interesting that this is kind of the most general way of describing boosting. The difference here is, or the idea here is that Adaboost minimizes the exponential loss, Laget Boost the log loss. What if I just have my own little nice loss function and I don't care about what? So I want my loss function minimized, and whatever loss function other people do, I don't care. I want my loss function. You can do this in general, right? You can say, hey, I have a general loss function, and this general loss function I can minimize by simply taking the derivative, the partial derivative of that, with respect to my function f here, right? So this loss function is, of course, a function of my true labels here and of my prediction f. And if there's a way of deriving that with respect to f, then I have this gradient thing here, right? And this gradient is a vector of length n, where n is the number of data points. And the only thing I have to do in every training round, I have to go in the negative direction of my gradient. This is just a definition of minimization. This is a very simple idea, right? And it works quite nicely. So if you implement that, it's really astonishing how well this works, right? And what you do is, of course, you in every training round, you only have weak classifier from the previous round. So what you do is you just evaluate it using your weak classifier from the previous training round, right? You say f minus 1. M minus 1 is the one that you just have in this round. You plug this in here and compute this gradient. And then you simply, once you have this gradient, your weak classifier simply tries to fit a mapping from x to your gradient. That's the trick, right? Now you don't have, again, you do regression. This is a regression function here, and it tries to be as close as possible to your gradient, right? Because then, if you do that, then you could sum up all the phi's, right? Summing up all these phi's is then very close to summing up all the gradients, and then you're again in the minimum of your loss function, right? This is the whole trick about it. So you sum up phi's with some factor here, some new factor here. Shrinkage is called. This is the shrinkage factor. And in the end, you just have this, the last sum after training around m. You just have a sum over all m regressors. Right? This is then your predictor. That's it, right? It's very simple. Okay, let's go a bit more into applications. As I said, Adaboost has been used for phrase detection, and this was probably the biggest impact that Adaboost had. The idea is to extract some features from the images. We use so-called HAR-like features, and train Adaboost on these features, and then use a cascade of classifiers. Features can be computed very efficiently. I'll show you how we can compute this efficiently. Then there's weak classifiers can be decision stumps or decision trees. And as inference in Adaboost, it's very fast. The phase detector can run in real time. This is a very important thing here, right? The training thing might be, where is it? Oh, let's not go back everything. Where is it again? Training could be kind of slow, right? Depending on how many training rounds you want to do, and how how intense is your weak classifier. How often you have to, or how expensive is it to do the weak classification? But inference is very fast. Inference means predicting, right? You have a new data point, and sorry for jumping. Yeah. So let's look at the features. These are the so-called HAR-like features. And these are features that are simple rectangles in your image, and you use one part, for example, of your rectangle to sum it up, and the other part to subtract it. Right? This is just a way of computing a feature from a small rectangle. You sum up all the pixels in this case, and you sum up the other ones, and then take the difference of these two, for example. Or here, right? So you have a black part and the white part, and one is the sum, and the other is subtracted from each other, and you can just do this. The good thing is that you can, so some of the pixels which lie within the white rectangles are subtracted from the sum of the pixels in the gray rectangles, right? This is the whole idea of these HAR-like features. You can write this also in this form here with integrals, but in the end it's just sums. So there's these kind of different types, right? You can, of course, imagine others, but these are these four types, A, B, C, and D. And, of course, you can also change the position where you compute these, right? If you have an all image, or if you have these are patches, right? This is a patch of your image. The outer rectangle is a patch. And then the question is, within that patch, where do you compute this feature, right? This is something else you can decide on. Now, there's a very fast way of computing these HAR-like features. This is called the integral image. The integral image simply computes first the sum over all pixels from the top left pixel to a given pixel, x, y, right? So you simply compute all these features here. And then with that sum, you can then compute all the sums that you need for a given rectangle by simply subtracting sums, right? So the integral on the rectangle D here, right? If you want to compute the integral of this rectangle here, you compute it in 4 axes to the integral image. We do this by taking the integral image at this position plus the integral image at this position minus the integral image at this position minus the integral at this position. That's the nice thing about it, right? You simply sum these 1 and 4, and you subtract 2 and 3. And this is a very efficient way to compute the integral image of D. Right? And this is nothing else, or this is all you need to compute the HAR-like features. Now, as weak classifiers, we have these 3 attributes. We can then define different types and size and positions of your feature. Then we have the threshold that tells us where in the feature space I have to do the separation. And I have a comparison operator that means it's a sign +1 or -1. This is just again, if you imagine your decision stump, one thing is of course to find the right separation plane, and then the other one is of course to find the sign that tells you which class is on the left side, which class is on the right side. And the resulting weak classifiers has then these parameters, right? The operation, the threshold, and the type of feature, size, and position. And X is like this X here is a 24 by 24 pixels window in the image. So we have a little window that goes over the image, and in that window you compute these features. This is, for example, something like that. So we have a face here, and this is one of these hair-like features which matches very well the eyes, right? This is something that comes out of Adaboost, right? Adaboost. The interesting part about Adaboost is, of course, that these weights W here, right? These tell you how good a classifier actually is, right? Right? This can be interpreted as a weight of the classifier, because if the error is very low, then this weight is very high, right? So this W here says how much do I trust one of my weak classifiers in every round, right? That's nice. So I do have weights for every data point, and the wrong classified data points have a higher weight, but also for the weak classifiers. Every weak classifier has a weight. You can call this a weight, right? And these weights then could be used to select interesting or very good weak classifiers, right? In this case here, weak classifiers is a feature like this here that separates the data, and these two actually are return a very high weight by Adaboost, right? Which makes sense because this is for face detection. It's very nice because this shows where the eyes are, this shows where the nose and the 2 eyes are. So this is very good. In inference, what you do is you have again your scale here, 24 by 24. Of course, there you don't know exactly the scale of your image, right? You don't know if the face is big or small. So there you have to do multiply with some factor and do this again, right? For each position in the image, you take your 24 by 24 frame. You try classifying the part on the image with the current scale using classifier selected by Adaboost, right? You just plug this into Adaboost. You look at if there's a face or not. And then you go on and increase the scale, right? Because you could have a bigger face or smaller face, right? Then there's another idea of this cascade. The cascade that has been shown also to make things much more efficient, right? So here you start with all sub windows and you classify them. And if you find this is not a face, then you stop, right? And this is just a way of doing this a little bit more efficient in this cascading things. I'm not sure if this is very important to say this here at this moment, but this is just the idea. Yeah, and these are the results. Yeah, you see these are some, and I think you all know that face detection today is something that is kind of solved, right? Many phones already have this, and it's just an algorithm that works very nicely. I don't know if the newer algorithms use still Adaboost, but this has been in its time. It was the big advantage of this, and it really brought the field forward. These are more results, and we're already at the end. I summarize the class of today. Boosting is a method to use a weak classifier and turn it into a strong one. And we have to really make clear the distinction between weak classification and strong classification. Weak just means it's a classifier that classifies, which has a classification error that is at most as bad as random, right? If it's worse than random, then it's not weak classified, and then you can't use it at all. So this means that almost like every classifier that you can use is a weak classifier. You could boost everything, right? That's nice. But in contrast, boosting algorithms like Adaboost are strong classifiers. And strong means that they have an arbitrarily small training error. You just add more training rounds to it, and the longer you train, you are better with your training error, right? So particularly Adaboost, what it does, it minimizes the exponential loss. And then there's other variants of boosting, for example, Laget Boost and Gentle Boost. These are more robust against outliers, and Gentle Boost works in general a little bit better. And we also had Gradient Boost, which is not here. Gradient Boost is just a very general way of doing that. Just have a general loss function and minimize that by just deriving that loss function in every training round with respect to f, right, to my prediction. Okay, and then we have seen some weak learners. A weak learner can be, for example, decision stump or decision trees, but there's other things, right? For example, yeah, I mean, as I said, you can use your favorite classifier as a weak classifier, as long as it has this property that that's not worse than random. Yeah, and then one example is phase detection that can be solved with boosting. Thank you very much. Questions?